All right, so welcome to the 10th lecture. So today we'll be trying to understand the central limit theorem and its connection to whatever we have done so far. For example, we have studied a lot of different things in this section. So we studied the convergence in probability, we studied the convergence in distribution, and today we'll be discussing the central limit theorem. Okay, but before doing that, so there was an unintentional error in the last class. So let me just clarify that from the last lecture. So this is from lecture 9. So let me just switch my camera. So in the last lecture, there is a very important thing. There is a theorem that we wrote that suppose that xn is converging to x in distribution and yn is converging to y in distribution. And then I didn't write this part. So what I wrote last time was then xn plus yn in distribution going to x plus y, which is not true in general. You have to assume that this xn's and yn's are independent, as well as this x and y are independent. Okay, so both of these are independent. So I added this. So xn and yn are independent for every n, as well as this x and y, wherever it's converging to, they're independent. If this holds, then this xn plus yn is converging to x plus y in distribution. So this is not true in general. Okay, so this is true under certain conditions. Okay, so with this, let's get started. And today we'll be using many results from the last class. So formally, this section is called the central limit theorem. Okay. All right. We have seen a version of it before, but let me just start by writing the theorem. So theorem, it goes like this. So let we have a bunch of IIDs. Let x1, x2, xn denote the observations of a random sample from a distribution that has a mean mu and a positive variance, and variance sigma squared. Also, it's a so we are assuming that this variance is finite. Okay, so then the random variable yn constructed by summation I from 1 to n xi. That means we are adding the n samples. We subtracted minus n times mu, where mu is the mean of each of those random variables. And we divide by square root of n sigma. Okay. In other words, you see that if I just divide everything by n, so this is nothing but 1 over n summation I from 1 to n. I'm dividing the numerator and denominator by n. So this is mu, and this becomes sigma over square root of n. You should, this should look very familiar. So this is really, the first term is x bar, and this square root of n goes to the top. So it becomes square root of n x bar, because this quantity is x bar, as we have seen. That's a sample mean, minus mu over sigma. So we construct is this quantity. So what this theorem is saying, this converges. So this yn, in other words, this quantity, it converges in distribution so this is in distribution. This is whatever we discussed in the last class. Okay, so there are two different kinds of convergence. One is convergence in probability and convergence in distribution. Here we're talking about convergence in distribution. So this is converging in distribution to normal 0 and 1. So it's converging in distribution to the standard normal distribution. In other words, so that is in our old notation, so x bar minus mu over sigma converging in distribution to normal 0, 1. And that's a very famous central limit theorem. Okay. We'll not prove it, but we'll be implementing this for various things. We'll prove a slightly different version of it based on this one, so which we actually used before. Okay, so one more thing that we sort of used this version before, right? So maybe if I write in a little different way, so just to make this a little more clear, so we use this version. So we reused x bar minus mu over sigma over square root of n. It converges in distribution to 0, 1. We didn't use this notation, but we considered this quantity, and we said that when n is large, this behaves like a standard normal distribution. So that's exactly this thing. And what is x bar? So x bar is the sample mean. Mu is the expected value of the sample mean. And this sigma over square root of n is the variance of the sample mean. So that is something we have seen. So basically what we have is x bar minus mu over the square root of variance of x bar is converging to this one. So let me just write that version too. So it really means that x bar minus e of x bar over square root of variance of x bar is converging to in distribution to normal 0, 1. So that is another version. Okay. So this is the square root of the variance of x bar. We have seen it before. All right. Now let's see what we can. I mean, we mentioned this theorem some time back, and in fact, if you recall, we used this for many different cases. But at the same time, we said that what if we, in many cases, if you recall, in the previous analysis, we replace this sigma by S. What is S? S is the sample variance. Okay, so sigma is the population variance. So the sigma over square root of n is the variance of x bar, but sigma is the population variance. Okay, so now in many times in the previous discussion, if you check, what we did is we replaced the sigma by S. And we said that this still holds true. So let's justify that. So now here is an example. It's called the large sample inference for mu. Inference for mu. It goes like the following. Let, just like before, so let x1, x2, xn be a random sample from a distribution with mean mu and variance equals sigma squared, where mu and sigma, or sigma squared, are unknown. Okay. This is typically what you encountered while testing the hypothesis, right? Now let X bar and S be the sample mean and sample standard deviation. Let me just I mean, since I wrote the central limit theorem in this way, I just remembered that just to show, I mean, what I wrote is absolutely correct, but I mean, just to show that this X bar will be depending on this N. So this just right here N. So this is just to show that this X bar is dependent on N. Now, for our case, when we are considering a sample, we don't really write this N. But since I'm writing a more general version, so it converges to, so let me just change all these X bars to N so that um, it looks somehow dependent on N. So as N is becoming larger, then it's going to the distribution. So I'm just changing all the X bars to N just to show it's dependent on N. Okay, so nothing more than that. Now, once you draw a sample, this N is fixed, so we just replace this by X bar. I'm just using I'm just thinking about this because now I'm not writing X bar because now this is for the so I'm just having an N fixed. So it is a fixed N random sample. So I'll denote simply by X bar the mean of that. Okay, so it's a sample mean, and this is sample standard deviation. Respectively. Once again, just to clarify what I said is N is fixed. So the number of sample is fixed. So we denote X bar N as X bar. So it's a notation. Otherwise, so, I mean, you can of course use N bar, I mean, you use a suffix N, that will not change anything. Okay, so we have a sample of size N, and we computed the sample mean, and we computed the sample standard deviation, or a square of this one is the sample variance. Okay, then the conclusion is X bar minus mu over S square root of N. It converges in distribution to N01 for large N. We'll prove it. But before doing that, let's see its similarity with the dissimilarity with the previous result. So it says that when N becomes large, I mean, of course, we are doing it for the fixed N, but that's why it's called the large sample inference. So we are saying that this is approximately normal when N is large. Okay, so because this quantity is converging to this one. Okay, now so the way we understand this is look at the last result, what we had. So we had this one. So let's look at this one. So xn bar minus mu over sigma over square root of n, it goes in distribution to n0. So it goes to standard normal distribution, right? So here for a fixed n, so this quantity is exactly x bar. Okay, as I said, it's just a different notation. So what I wrote later is for a fixed n. So this is x bar minus mu. So what is really curious is now we are replacing this sigma by s. And still this quantity is going to standard normal. So that's the most powerful or that's the most subtle feature of this theorem. It says that when I replace that sigma by s, because this is really xn bar, but when I replace that sigma by s, it still holds true. Okay, here's a proof. Let's compute this quantity. So say x bar minus mu over s over square root of n. I can write this with the notation from the last one. So it's x bar minus mu over sigma over square root of n. Now let's see what we added extra. So we had a sigma here, which was not there. So I have to multiply by sigma. I need an s here. So it's sigma over s, right? Right. So now let me show you one of the results from the previous one. So from one of the previous classes. So we proved before. By the way, remember that this x bar is same as x bar n. Okay, so it's the same as x bar n. So since we are having a fixed n for large n, so we are just writing x bar. Okay, we proved before, and I would request you to check lecture number 8. Okay, so there we proved that S converges to sigma in probability. In fact, we proved S squared is converging to sigma squared in probability. That means S is converging to sigma in probability. Okay. Therefore, I can write S over or sigma over S is converging to 1 in probability, to number 1. Okay. So this is by using various results of the previous section. So for instance, this is true, then we can write sigma is converging to sigma trivially. And then we can use the fact that 1 over sigma is converging to 1 over sigma trivially. And then remember that if a sequence xn converging to say x and a sequence yn is converging to y, then xn times yn is converging to x times y. Okay, so that is something we studied in the 8th lecture. So basically, and by the way, for that, we don't need anything like independence. So what we really are doing is the following. So that this really means that 1 over sigma converging to 1 over sigma, it's also trivially. And then if I take this one and multiply, and I'm using this result. So xn converging to x in probability, yn converging to y in probability, then xn times yn is converging to xy in probability. Okay, please note that no independence is needed for this one. Okay, so no independence is needed, unlike the probability in distribution that I sort of clarified at the beginning of today's class. So for this one, I don't need any independence. So therefore, I can simply take this one and multiply. So S over sigma is going to sigma over sigma in probability. So it is, or again, it doesn't matter. So I can write 1 over S is going to 1 over sigma, whatever I want to write. So basically, all these combinations are going to 1. Okay. Okay. So this is fine then. So we check that the sigma over S or S over sigma is converging in probability to 1. Okay. Now, what do you have? So basically, I have something which is going to a constant, and this quantity. So we already know that also x bar minus mu over sigma over square root of n. So what about that quantity? So this is going to the normal distribution. So it's normal 0, 1 in the distribution by central limit theorem. So sometimes the central limit theorem is abbreviated by CLT. That is something we already wrote, right? So what we're writing is this part is going in distribution to the normal distribution, right? So next, we'll be using the Slutsky's theorem, which I have it here from the last class. So it goes like this one. It's right here. Look at that, what it says. So that it says that if xn is going to X in distribution. AN is going to A in probability, BN is going to B in probability, okay? So suppose we, for a moment, forget about AN. So suppose this is 0, this is 0, okay? So this theorem is saying that if BN is going to B in probability, so B sub N is going to little b in probability, and X sub N is going to X in distribution, then B sub N times X sub N is going to little b times X, right? Now we have exact same scenario. So where my B sub N can be thought of this sigma over S. So it's going to 1 in probability. And then we have X sub N, which is something like this one, which is going to the normal distribution, the standard normal distribution in distribution. Then if I invoke Slutsky's theorem, it would mean that, forget about N because I'm just assuming all this 0. So that would mean that this quantity right here, it would go to 1 times the standard normal distribution in distribution using the Slutsky's theorem. So hence, by Slutsky's theorem, we can conclude that. So by Slutsky's theorem, we conclude that this quantity that we wrote, x bar minus mu over s over square root of n, which is sigma over s times x bar minus mu over sigma over square root of n. So this is going to 1 in probability, and this is going to the standard normal in distribution. So that means this whole thing is going to, and here we are using Slutsky's theorem, to standard normal in distribution, okay? So because there are two different kinds of things going on. So one is in probability, one is in distribution. So the result is in distribution because of this. Okay. Now this actually, this is something we have used a lot for all the previous discussions. So we were somehow using some forms of it, okay? Because we always replaced the sigma by S, if you recall, the sample mean, and then we computed this quantity for n large, and then we considered this one. So that's why it's called a large sample approximation. Okay, now let's do an example. So here is an example. So let x bar denote the sample mean, the mean of a random sample of size 75 from the distribution X that has the PDF fx equals 1, provided 0 less than x less than 1, and 0 otherwise. So that means what are we trying to do? So we are saying that x bar, it's the mean of the random sample and of size what? Of size 75. And so that means x bar is really computed. If I want to write it, it's 1 over 75, I from 1 to 75, xi. What are those xi's? So xi's follow the distribution of, so xi and x are same in distribution. And what is x? Its PDF is given by this one. Okay, so that means if I want to compute the, let me just write the problem. It's very difficult to compute the PDF of X bar because it's a mess, right? So in this situation, so difficult to compute uh, to compute the PDF of X bar, right? Because there are 75 additions, it's a convolution, and then you have to, I mean, they're independent, so you can have the sum of two random variables, but it's difficult. And consequently, suppose I want to compute, say, probability of minus 0.45 less than X bar is less than 0.5. It'll be very tough in the sense that I don't know if X, it's ideally computable. So I don't know the problem. So PDF of X bar is a mess. And consequently, if you want to compute this, it's basically you have to integrate the PDF between these two numbers, and the PDF itself is very hard. It can be shown that it has I mean it's composed of arcs of 75 different polynomials of degree 74. So it's a very laborious computation. We'll not try to do it. Okay, so it's I mean extremely laborious if you want to compute it from the scratch. However, luckily, using the central limit theorem, we have bypass. Okay. Let's compute, however, we can approximate this with the central limit theorem. For that, I have to first compute. So what do you need? So for computing this using the central limit theorem, I have to know if I use this version. So remember, xn bar is same as x bar in our case because n is fixed 75, which is a very large number, right? I have to compute mu, I have to compute sigma, and n is 75, right? So let's compute mu. So how do you compute mu? So mu is the expected value of X bar. Okay. Now, I have a very easy way of computing this. What is that? So this is really, if I look at this expression, so this is basically 1 over 75, I from 1 to 75, E of xi, right? And there all these expectations are same. So it's 75 times E of xi over 75. So I can replace xi by anything I want because xi's are iid. So it's basically, I can write simply x1 as xi's are iid. How do you compute E of x1? Well, E of x1 follows this distribution, right? So it's very easy to compute. So basically what I want to do is I write x fx dx. Fx is the same fx, so this fx, between 0 and 1. And this is really 1, so it's basically 0 to 1, x times dx, so it's x squared over 2, so that means it's 1/2, right? So mean is 1/2. Similarly, I can compute the variance of the sample. What is the variance? So sigma is really, it's for using this distribution, sigma squared would be integration of 0 to 1 x minus 1/2 squared and then dx, fx dx. So that is how we compute the variance. So basically fx is also 1. So this is 0 to 1 x minus 1/2 squared dx. And if you compute that, that is going to be 1 over 12. Okay. So we found the sigma and sigma squared and mu, and then I can approximate this for using the large sample approximation. Hence, that probability that we are trying to compute. So hence probability of 0.45 less than x bar less than 0.55 can be approximated by, I mean, first of all, this is, let's convert this to the, with the appropriate mu and sigma. So let's write this as x bar minus mu over sigma square root of n. That's what we want. Okay, so it's basically I want 0.55 minus mu over sigma square root of n. This is less than 0.45 minus mu over sigma square root of n. So I want this quantity, as we have done many times before. Now, in our case, n is 75, right? And mu is 1/2. Sigma squared is 1 over 12. If you plug everything here, you'll find that this is going to be probability of this quantity would be minus 1.5 less than, let's keep it this way, x bar minus mu over sigma over square root of n. Of course, you're welcome to use the values of mu and sigma, but it's not really that important. So it's less than 1.5. Okay. So if you compute that, you'll see that you'll end up with this one. Now, this is approximately, this here the approximation comes. So it's a large sample, approx, with the central limit theorem. Why? Because we know now this quantity in the large sample will behave like z, which is normal, the standard normal distribution. In distribution, it will be same as z. So that means I can approximate this as phi of 1.5 minus phi of minus 1.5. The phi is the CDF of z. We have discussed this notation a lot of times in the previous course. If you compute this, you'll get 0.8663. Okay. So what we found is, so probability of 0.45 less than x bar less than 0.55 is approximately 0.8663. And this is good enough because, I mean, I don't need to compute the sum of 75 variables and then get the convolution result and then compute this probability. So this approximation is good enough because the sample size is pretty large. Okay. All right, so this is the first one. Let me just, at this point, let me just solve another problem from the exercise. And this is, let's consider, say, the first one. So this is example, and it's from exercise 5.3.1. It goes like this. Let x bar denotes the mean of a random sample of size 100 from a distribution that is chi-squared with 50 degrees of freedom. So chi-squared 50. Compute the quantity probability of 49 less than x bar less than 51. Okay. Now, of course, you can compute this with the chi-square distribution, but it may be a little tedious. So instead, what we'll be doing is that we'll be using the central limit theorem. So let's do that. So for this problem, let me remind you, here is a solution. So remember what is the expected value and variance of chi-square with the degrees of freedom r? So we know that expected value of a chi-square with degrees of freedom r is r, and variance of a chi-squared with degrees of freedom r is 2r. Okay, check the first lecture. So we wrote this result there. Okay. So that means for our case, x bar, E of x bar would be 50, because it's so it denotes the mean of a random sample of from the distribution of chi-squared, right? And the variance of x, so basically what I'm writing is the following. Um, so for what I really meant is x bar is given by, it's from a random sample of size 100, right? So it's basically 1 over 100 summation I from 1 to 100 xi, where each of these xi's, so where what we have is where xi's follows chi-squared with degrees of freedom 50, right? So this is very easy to show because if I take the E of x bar, it's basically E of x1 same, and the expected value is 50. And also, what is the variance of xi same? So variance of xi for every I is 2 times 50, which is 100 for every I. 100, right? And therefore, what we do here is the following. If we use the central limit theorem, we can write that x bar minus its expected value, that is 50, over the variance of the individual ones, 100, square root, over n, which is 100. Okay, so over square root of n. So I'm trying to write this one. X bar minus mu over sigma over square root of n, which is equal to, so x bar is x bar, mu is 50, which is this number, sigma corresponding to the elements which is consisting of the sum, so corresponding to the random variable. So for every random variable, so it's sigma. So here we found it's a 100, it's square root of 100, and then we have to write square root of, so we have 100 sample. So because n is 100. Okay. So basically what I'm using is, I'm using this one as sigma square and this one as mu. Please note that even if I compute E of xi, that is also 50 for every I. I mean, you may wonder why I'm using two different notations. But here, E of x bar is 50, which is same as E of xi for every I. But here, the variance of xi is actually 100, but variance of x bar is 100, 100 over, I have to divide by n. Okay, so this quantity is what? So this is really in distribution, it goes to, since n is a big number, it goes to the standard normal distribution, right? And therefore, I can compute this quantity, what they want. So I can compute this P of, so that means what I'm saying is this is x bar minus 50 is converging in distribution to n, the standard normal distribution, right? Hence, if I'm trying to compute probability of 49 less than x bar less than 51, that is same as probability of x bar minus 50 less than 1 minus 1, right? By this fact, we know that it's going to a standard normal distribution, And hence I can write this as phi of 1 approximately. So this is approximately phi of 1 minus phi of minus 1, using the fact that x bar minus 50 follows the standard normal distribution. And if you compute this, it's about 0.683. And that's the answer. So what is the probability of 49 less than x bar less than 51, where x bar is the sample mean of a sample which is drawn from a chi-square distribution? So basically, I mean, this is given by approximately 0.683. And this is a direct application of the central limit theorem. Okay. Let's do one more. So let's compute, say, the negative, the second problem in the list, which is example which is from exercise 5.3.2. So it goes like this. Let, just like before, let x bar denote the mean of a random sample of size 128 from a gamma distribution, which again we studied in the first class. We roughly studied in the first class, with alpha equals 2 and beta equals to 4. The question is to approximate probability of 7 less than x bar less than 9. Once again, this can be computed, but this is a very laborious computation, so we'll approximate this. Okay, so here is the solution. So, so if x follows the gamma distribution with parameters alpha and beta, then it is well known that E of x, I think we wrote it in the first class, it's given by alpha beta, and variance of x is given by alpha beta squared. And what we have here is basically x bar is, it's from 128, so it's 1 over 28 summation I from 1 to 128 xi, where xi follows this x, the distribution of x, which I wrote here. So that means E of xi equals to the E of x, which is alpha beta, and variance of xi is variance of x is alpha beta squared for I equals to 1, 2, 3, 128. That is my n. So n is 128. That's the setup. Now it's very easy. So what we need to do is I'm trying to approximate something. So let's compute this. So we have x bar. So in our case, so what is alpha and beta? So alpha is 2, beta is 4. So this is 8, right? And then it's 16 times 2, so it's 32. With alpha equals to 2, beta equals to 4. Right? Therefore, let's compute the quantity of interest. So x bar minus its mean, which is alpha beta, over, we have to write alpha beta squared square root. That's the sigma, right? So this is our sigma squared, and this is our mean, mu, over square root of n by the central limit theorem. This goes in distribution to the standard normal. Alpha beta, we already have 8. Alpha beta squared, we have square root of 32. And then square root of n would be square root of 128. Right? So that means x bar minus 8, and this is square root of 32 over 128, which is 1 over 4. So this number is going to 4. So it's square root of 4, it's 2. So what we really have is 2 times x bar minus 8 is going in distribution to the normal distribution, to the standard normal distribution using the central limit theorem, because n is large. And then as soon as we get it, the rest is very easy. So I'm trying to compute this probability, right? So let's write this down. Hence, the probability that we are trying to compute, probability of 7 less than x bar less than 9. And I'm trying to match this with whatever we got. So we have x bar minus 8 times 2, right? So this is equal to, let's see, I have to subtract 8 and multiply by 2 everywhere, right? So I have to subtract 8 multiply by 2 here. I have to subtract 8 multiply by 2, which is really, this is, I believe it's minus 2. This is 2x bar minus 8, and this is 2. And we know that this is going in distribution to normal distribution, to standard normal distribution. And hence, I can approximate this as phi of 2 minus phi of minus 2, which if I compute with the table, it is approximately 0.954. So the probability that x bar is between 7 and 9 is 0.954, for which x bar, where x bar denotes the mean of a random sample of size 128 from a gamma distribution. So this is a way, this is a very powerful way of computing some probabilities or approximating some probabilities using the central limit theorems. All right, now, so at this point, let's talk about the binomial distribution a little bit, because it's a little bit special. Okay. So it's called the normal approximation to the binomial distribution. So it's a normal approximation to the binomial distribution. Okay. Now suppose that we have a say x1, x2, xn is a random distribution, or sorry, it's a sample from a Bernoulli distribution, Bernoulli P distribution. So that means for every outcome x1, x2, xn, so there are two possibilities. So outcomes of x1 can be 1 with probability p, 0 with probability 1 minus p. Same is true for x2 and so on. Okay. So therefore, we know that the mu is p, and sigma squared is 1, p times 1 minus p, right? That is the mean and standard deviation for a Bernoulli distribution. Now consider, so hence, this is known fact. And by mu, I mean the expected, so the mean of individual x's. Okay. So consider now, say, the sum of xn's. We know that in this case, we say that yn follows a binomial distribution with parameters n and p. So this p is same as this p, and this n is whatever we are summing over to. So that means if you have n trials, so this counts the number of success in n trials, because you see that if there is a failure, then xi values are 0, so it doesn't count that success. I mean, so basically yn counts the number of success, so it counts the number of success in n trials. So this is a known fact, even from a previous course. Okay. So also observe that what is the expected value of this thing. So also E of yn is really np. We know that. And variance of yn is n times p times 1 minus p. Known from some previous course. Okay. Now let's check one of the versions of the central limit theorem that I wrote. I mean, there are various versions. So it really says that if I have a random variable, so if I have a random variable, if I subtract the expected value, divide by the square root of that random variable, it always goes to the normal distribution, right? So if I use that here, hence, so if I just want to compare it with whatever we had before, so yn is kind of similar. If I want to make this yn kind of similar, then let's see. We have yn minus np, which is the expected value of yn, over the square root of the variance, so which is n times p, 1 minus p. Let's massage this a little bit. I can write this as, if I divide by n, so it's 1 over n yn minus p. And if I divide by n, so what I have is square root of p 1 minus p over square root of n, right? So I divided the numerator and denominator by n. Now, what is yn over n? So that is, for this sample, it's, so therefore, yn over n is equal to 1 over n summation of this one. So which we denote as, say, xn bar. Once again, if the sample is fixed, number of n is fixed, then I can just write it x bar. So this is really what we are having is a yn over n. So I can write this as xn minus p over whatever we have. So this is the sigma. We call this one the sigma, right? So let me just write it one more step. 1 minus p, and then square root of n. Right this way. So all I did is I replaced this xn. Now, basically, so what is this xn bar? So xn bar is really 1 over n summation xi, I from 1 to n. Now, this should remind you of the format. So I mean, I should be able to, so this p is the expected value of mu, so of all these xi. So I can write this as xn bar minus mu. So this p is same as mu, which I defined earlier. So those are for this xi's, right? So where the expected value of xi's are called the mu's, and variance of xi's are called the sigma squared. Of course, we know those. So variance of xi's is p times 1 minus p squared. Sorry, p times 1 minus p. So it's the square root of the variance. So it's going to be sigma square root of n. Now this format is something which is very familiar to us. So it is going in distribution to the standard normal. How? By the central limit theorem. Right? So that means we have this quantity. So from a, so this is called the binomial. So this is called the normal approximation of the binomial. Okay. Now, typically, what happens is if I have a histogram for the binomial distribution, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just drawing a distribution for the binomial case. So if I have something like this one, I mean, remember the histograms for the case of the binomial distribution is drawn this way. So something like this one. So if it's the histogram, so this is the for histogram for binomial. So there are so its trials or number of trials are basically 10 with certain probability of success, P. Okay. So this may look like this one. So I can have out of 10 trials, you may have, so let me just add here 0, this one. So we have a minus 1.2. Okay. So typically here the point is typically when we draw a histogram for say 10 trials, so we always draw the histograms from, for example, for the frequencies corresponding to 0, so number of times you get a 0, you start the histogram from minus 0.5, you end with 0.5. So it's 0.5, it's minus 0.5. Once again, for the histogram for the frequencies for 1, you start at 0.5, you end at 1.5. For the frequencies for 2, you start at 1.5, you end at 2.5. So, and if you want to count the number of 2s you get, you just count the bar, which is the top part of this bar between 1.5 and 2.5, and it's true. Now, when you approximate this with a normal distribution, so it looks something like this one. So it looks something like again, my drawing is bad, but it tends to go through this. Okay. So this may be a picture for the normal, so NP, so it's 10P, comma, the variance is 10P 1 minus P. Okay. So you see that, suppose I'm trying to compute, say, if I want to compute the probability between, say if I want to compute, say, probability of the binomial history, so this is my y, and this is my approximating version, which is when I approximate that with a normal version. So essentially what I'm having is, if I want to compute, say, 3 less than y less than 5, okay, and where this y is in binomial distribution. So if I wanted to do it from this table, I simply count the length, I mean, how many frequencies is here in 3, how many frequencies are here in 4, and that's it, right? So 3 and 4, so those frequencies are consisting of the total number of frequencies. Now, if I approximate this with the normal curve, so the normal curve is going somewhere from here. So it is somehow passing through the midpoint, not through the midpoint, around the midpoint. Okay. So if I just write this equal to for the normal distribution, so let's call this one n prime. So if I write this way, say 3 less than n prime less than 5. Okay. Now there's a problem. The problem is the n prime for 3 is here, and n prime for 5 is here. Okay. So it's not really computing the area that it's supposed to compute, because I'm asking it to compute this area, this and this. Okay. But if I compute this n prime between 3 and 5, it's really computing the area from here to here. Okay. So that's the problem. So this is not a good approximation. Good approximation. Okay. So instead, so this is something called the continuity correction. When we go from binomial to normal, that is the correction we needed. So I'll write the following with. So it's 3y5, where y is again binomial. So see that. So I want to compute this area plus this area, right? So why don't we write this from 2.5? So there's a curve which is going through 2.5 and it's say ending at 4.5. Okay, so it's same as approximately same as, so this is not good. So approximately it is same as 2.5 less than y, sorry, there's an n prime when I'm having this bigger curve, less than 4.5. Why 0.5? Because approximately this normal approximation is going through 0.5, like it's going through the halfway of these histograms. Okay, and hence you see that this is a better approximation. Approx. It's still an approximation, but it's a better approximation because it's closer to the speed, because now I'm integrating the curve between these two. So which is really what we want. This is due to the fact that whenever you draw a histogram, so you have like always these numbers are off by 0.5 for the histograms. And that's why maybe this one, which is the normal curve, which is approximately the histogram, you compute this way. Okay, so in other words, so here's the in general version of the continuity correction. So in general, the continuity correction for normal approximation of binomial distribution is given by if P, say A less than Y less than 5, where Y follows, say, a binomial distribution. We can approximate this by writing A minus 1/2 to N prime less, sorry, this is 5, not 5, I meant B. Okay, so it's B so it's B minus 1/2. So here this is normal. A more practical version of this one is the following. So usually if y is less than b for the case of binomials, this really means the probability of a less than y less than equal to b minus 1, right? So that means this is because, I mean, y can be only integers. So this is approximately a minus 1/2 less than n prime less than b minus 1 plus 1/2. And usually this version is used more often, which says that you have to subtract half from the lower endpoint. And if you have this equality sign, you have to add 1/2 to this one. Okay, but if you have a less than equal to less than sign, strictly less than sign, you're subtracting. All right, so this is called another. Let me just write this way. So probability of A less than suppose we have A less than equal to Y less than equal to B, which is again approximately equal to probability of A minus 1/2 less than, less than N prime less than B plus 1/2. You should remember this version. This is binomial, and this is normal. And this 1 minus 1/2 and plus 1/2 are the continuity correction. Okay. All right, so let's study one example on this one. So here is an example. suppose n equals to 100 and p equals to 1/2. And we want to compute with the old notation, probability of y equals to 48, 49, 50, 51, and 52. Okay. Now, therefore, I can basically write that I want to compute y is a discrete random variable, so it's a binomial random variable. So here y follows a binomial distribution with parameters 100 and 1/2, right? So there, you can think that about like you have a fair coin, you are tossing it for 100 times, and you are trying to observe the number of heads. So the question is, so what is the probability that you will be observing 48, 49, 50, 51, or 52, or everything's all heads? Okay. So now I can write this approximately as say 48 less than equal to y less than equal to 52. Right? For the binomial case. So by the previous one, so therefore I can write this as, so its mean is what? So I can now compute the mean of this one. So E of y is NP, which is 100 times 1/2, which is 50. And the variance of y is 100 times 1/2 times 1/2, which is 25, right? So this really means that we are trying to compute probability of y minus 50 over the square root of the variance, which is square root of 25. So this is true. So it's 52 minus 50 over square root of 25. Here, the same thing, 48 minus 50 over square root of 25. So far, I didn't do any continuity approximation because my y is still a binomial distribution. But now I'm thinking this y minus 50 over 25, it's approximately normal. Okay. Now, if I consider this approximation, I have to change the limits, right? So let's, I mean, if I did that, so then I have to change the limits. Let's change the limits. So what we will have is the following. If we want to use the continuity approximation, if we want to approx with normal, then what we'll do is the following. So probability of 48 less than y less than 50, less than 52, it's approximately, I mean, this is actually exactly probability of 48 minus 5, 48 minus 1/2 less than y less than 52 plus 1/2, right? Still y. Because why is this true? Because when you compute the y is still a discrete version. If I approximate this with the normal distribution, so I'll have 47.5 less than, strictly less than n, less than 52.5. So here n is the normal distribution. So n now, it follows the normal with mean 50 and variance 25. Right? I can compute this now. So it's probability of 47.5 minus 25, minus 50 over square root of 25 less than n minus 50 over square root of 25 less than 52.5 minus 50 over square root of 25. So if you compute this, you'll get probability of minus 0.5 less than, this is now approximated by z, because you're subtracting the mean divided by the variance for this normal distribution, right? And if you compute this one, it's 0.5. And we all know how to compute this. So this is basically phi of 0.5 minus phi of minus 0.5, which if you compute, it's 0.3829. This is our approximation of this value. So you see that this quantity y is it follows a binomial distribution. So its computation is very laborious in the sense that if you want to compute this, it has all those combinatorics symbol, and then we compute it accordingly. But with this, we can pretty easily compute it. Okay. So let's do an example on this one too. So this is say example number 5.3.3. So example. So it is exercise 5.3.3. It goes like, let y follows a binomial distribution with parameters 72 and 1/3. That means this is n and this is p. Approximate probability of 22 less than y less than 28. Okay. So therefore, solution. So here we have E of y is NP, which is 72 times 1/3. So this is my N and this is my P. So 72 times 1/3, which is 24. And variance of y is N times P times 1 minus P. If you multiply 72 times 1/3 times 2/3, it's going to be 16. Right? So we know the E of y and variance of y immediately. Now, so therefore, what we know is this quantity let's start here. So probability of 22 less than y less than 28 using the continuity approximation, because eventually we'll be using the normal distribution. You can write this as probability of 21.5. We subtracted half from here, less than equal to y, still less than equal to 28.5, because it's still a discrete version, right? Now, this is same as if I just approximate this with a normal distribution. This is same as our approximately probability of, let's see, 21. Let me just do it here. Approximately probability of 21.5 minus its mean, which is 24, over square root of 16. So y minus 24 over square root of 16 less than 28.5 minus 24 over square root of 16. Okay. So note that I'm just keeping this y in the same way with the understanding that now I'll be doing the normal approximation. I mean, ideally, I mean, you should use a different letter. Like here, we went from y to n because now n is normal. But I'm just using a little abuse of notation, saying that, I mean, this y was here the binomial, and here I'm thinking about a normal approximation. So I'm just keeping the same y, okay? You're welcome to use a different letter for here, but it's an approximate version. Okay. What I have here is, therefore, we know that this quantity is standard normal, right? So that means this is equal to probability of, if you compute this one, it's going to be minus 0.625 less than y minus 24 over 4, which is z, which is less than 1.125. So approximately. So this is going to be phi of 1.125 minus phi of minus 0.625. If you compute this from the table, you get 0.532. So that is the approximate value of this one. Okay. So once again, you started with a binomial. You first did the continuity approximation, and then you just kept the same variable name, but you pretend, I mean, you were assuming that now this y turns into a normal distribution. So you have all the less than sign, and this is how it works. Okay, so this is how the binomials are approximated with the normal distribution. Now, in a very similar way, we can use our large sample approximations for many other things. So, for example, the large sample approximation or inference for proportions. Let's see how it works. Let x1, x2, xn be a random sample from a Bernoulli distribution with p as the probability of success with parameter p. That means the probability of success is p. Okay. So that is the probability of success for each of these x1s. For example, you can think that you're tossing a coin, and this is the probability of success of getting, meaning that probability of getting a head. So let p hat be the sample proportion of success. That means we observed a success. So we found a sample. And what is this p hat? So number. So p hat is basically number of successes in a sample over the total number of points in sample, which is n. That as simple as that. Okay. We have seen before that then we can basically x bar can be written as p hat. Okay, so the sample mean is that this number. So basically, we are computing the number of successes and dividing by n. So essentially, what we did here is this is nothing but 1 over n summation xi, I from 1 to n, isn't it? Which is really x bar. So p hat is really x bar. Hence, by the central limit theorem, this p hat, which is x bar with understanding, minus its expected value is p, and its variance is so okay. So the variance for the sample from where it's taken is p1 minus p, right? And then if I divide by square root of n, so that goes to the standard normal in distribution. So that is true because as the expected values of xi's are p and variance of xi's are p times 1 minus p for I equals to 1 to n. They're from this, there are IIDs. Okay. Now also observe that, so this is for the, so here p and 1 minus p, this is from the population, but also if we observe the population variance, which is what? So also in this case, S squared is P times 1 minus P for the population. Sorry, P hat 1 minus P, isn't it? So that means when you're drawing the sample, when you're drawing this particular sample, then you can, suppose we have this x1 through xn with mean of this one P hat. So the variance, if you're trying to estimate the variance of this x1, x2, xn, so your estimator for x bar is P hat, so that is the sample proportion. So that means we can estimate with this one, right? And hence we can by the one of the theorems that we written earlier. Let me show you this one. So if I just replace the population variance by sample variance, here S is the standard deviation, but its square is a variance. But if I replace the standard deviation of the population by the standard deviation of the sample, it remains the same thing. We have shown it. Right? So hence, by a similar argument as before, we can also conclude that if I replace these p's by p hats, meaning that if I have p hat minus p over square root of p hat 1 minus p hat, and then over square root of n, that also in distribution goes to the standard normal distribution. Both are true. So p hat minus p over, if I have just p, that goes to normal distribution, standard normal. Also, if I replace the denominator by p hat, it's the same. Okay. Another example. So suppose we have chi-squared. This is something also we have done before. So suppose we have yn, that is binomial distribution with parameters n and p. Okay. Then we have seen that, for yn minus np over square root of np 1 minus p, it converges in distribution to the standard normal distribution, right? Now, what is the square of a standard normal distribution? So the square of this standard normal distribution is the chi-squared distribution, right? So also remember that we have observed this one. So last time we have proved this one. Let me just write it. We have seen that suppose xn is a sequence that converges to x in distribution, and g is a continuous function on the function on the support of x, then g of xn is also converging to g of x in distribution. We have seen that. So now we know that suppose we have the function, say, g of x equals to x squared. This is converging to standard normal. We know that the square of the standard normal is chi-squared with degrees of freedom 1. And hence, we can say that yn minus np over square root of np 1 minus p squared is converging in distribution to chi-squared. Now, please note that we're not doing any hypothesis testing here. So we are just saying, saying that for this binomial distribution, so we already know what n is and what p. So there is no hypothesis testing here. So n is known, p is known. So that means that no hypothesis testing here. So all we are saying that we know that this is going to the standard normal, so its square is going to the chi-square, and we are now we know that from all the previous theorems. Okay, So that is pretty much all about the central limit theorem and its applications. So next time, with this background, we'll be considering something. Um, we'll be dealing with some more um, inference, like hypothesis testing and drawing some inferences from some tests. We'll be dealing with a lot of new materials, but this is pretty much the content of chapter 5 in the textbook. And from the next time, we'll be starting a new chapter. So thank you.